Hi everyone. In today's video, we will be solving a numerical problem end-to-end using the ID3 decision tree. The problem statement will have both numerical and categorical attributes. And this problem is an unsolved exercise problem taken from a very good book in data mining called as Introduction to Data Mining by Tan, Steenbeck and Kumar. It consists of both categorical and numerical feature attributes. There are repetitions in the numerical and categorical feature values, and it is a binary classification problem. You can see that the attribute A1 and A2 are categorical in nature, A3 being numerical, and there are some repetitions in the numerical attribute, like the value of 7 is being repeated over here. And we will consider this as a binary classification problem, with the positive class being represented by 1 and the negative class being represented by 0. As discussed in the part 2 of this video series, we will start with the entropy before performing a root node, which is the overall entropy of the data. For this, we see the count of 0 and 1 in the target. We encode positive values with 1 and the negative values with 0, and we use the usual formula of finding the entropy before forming the root node. We can clearly see that out of the 9 values available, 4 are positive as represented over here, and the remaining 5 are negative. We plug in the usual entropy formula which we know, and we get the entropy before forming the root node to be 0.99108. We will now proceed with individually finding the information gain corresponding to attribute A1. For that, we first need to find the entropy corresponding to A1. The information gain comes out to be this. So we consider the attribute A1 and we find out the probability of 0 and 1 as we used to find out previously, corresponding to each of the distinct values of A1, true and false. And we get the weighted entropy as 0.76 over here, and the information gain, if we have to calculate, we will consider the entropy of the root node which we calculated over here. We deduct the entropy corresponding to A1, which is the weighted entropy, and we were able to find the information gain corresponding to A1 to be 0.22948. We are going to perform a similar operation for the attribute 2, which is again a categorical variable similar to attribute A1, and we get the following result. So as you can see, the information gain corresponding to attributes A2 is 0.007, which is much less than A1. We can consider A1 for splitting the root node, but we still have one attribute more left, A3, which is numerical in nature. And now things tend to become a bit interesting over here. We have a numerical attribute A3. We have discussed in part 4 of this video series as to how to handle such numerical attributes or features. If we see the column A3 carefully, we see there are some values in A3 which are getting repeated. However, we will consider only the distinct values of A3 and arrange them in an ascending order to obtain the following sequence. So we can clearly see that all the distinct values of A3 are arranged over here, and the corresponding split points are attained over here. So these are the split points which are obtained on finding the midpoint of two successive values of the sequence written over here. For instance, 2 is obtained by considering the midpoint of 3 and 1. 3.5 is obtained by considering the midpoint of 3 and 4, and so on. So we consider two extreme values as well, 0.5 and 8.5. Even though we can exclude it, but just for the sake of convenience, we will include it. And in later stages, we will also explain why exclusion of these extreme values is necessary after the root node is formed. So if we proceed further and by following what we did in video 4 or part 4 of the video, we get the information gain corresponding to A3 as below. So we clearly see we considered various split points, we considered the distinct values over here. We also kind of considered the entropy and the overall entropy. And if we scroll down a bit further, we can find the maximum information gain which we can get from this data, which is attained somewhere at split point 2. So which is 0.1429. So this is how we were able to get the entropy corresponding to attribute A3. Now, if you see carefully, we got three entropies over here. The information gain corresponding to attribute A1 is 0.22948. The information gain corresponding to A2 is 0.007. Now, if we consider A3, the highest information gain we are getting at 0.14269. I will urge you to redo the calculation just to verify the results which we are getting over here. I will pause the screen a bit. Meanwhile, you do the calculations. But it's very clear what attribute we are going to split to form the root node. So this is how the decision tree formation looks after the first iteration. The root node is A1 as we were able to find out. And we take two values T and F, which are the two distinct values of A1. We consider the true values and false values over here, and consequently split the data on the basis of A1 to D1 and D2. D1 consists of all the data points, which is the subset of the actual data set, where the value of A1 is true, and D2 is the data set corresponding to the actual data set where the value of A1 is false. Now, if you consider all these cases where the value of A1 was false and we try to subset it, we exactly end up with both D1 and D2. So we proceed with D1 first. It has two features for which entropy needs to be determined, A2 and A3. We won't be calculating entropy corresponding to A1 because all values corresponding to A1 in the dataset D1 is true and we can't split it further. So as we proceed further, the information gain corresponds to A2 will look something like this. The information gain comes out to be 0.26 over here. And this is the information gain corresponding to attribute 2 A2. We will calculate the similar information gain corresponding to attribute 3 as well, and since this is numerical in nature, we will proceed in the same way as we did before for the calculation. So there were four distinct values in A3, 1, 5, 6 and 7. We consequently get the split points 0.5, 3, 5.5, 6.5 and there is 7.5. So both 0.5 and 7.5 are the extreme points. We should note that while we can calculate the entropy for values 0.5 and 7.5, it is better not to do it because we won't be gaining anything much from there. Selecting such extreme values as split points will mean that we are getting the entire dataset again as it is to split, which will make no sense. So if I consider the calculation table, even though we can write the calculations corresponding to these extreme values, but these will have much less of a practical implementation. The entire focus should be on the values which are in the middle, like 3, 5.5 and 6.5. So now if we see carefully the information gain, the maximum information gain over here is 0.0729. And now if I look at the maximum information gain corresponding to A2, it was 0.2616. It's clear from this example that if D1 has to be split, it has to be split entirely on A2. Now since we are able to split D1, we get a decision tree which will be looking like this. So this is a decision tree after splitting the data set 1. Now just look carefully at the entropy which we are getting at each stage. So at the root node, the entropy was 0.76. Now we selected A2 for splitting, the entropy came out to be 0.5. And we are yet to find the node which is supposed to be there at this place. That's we are yet to find out the node which we are going to select for D2. Now we will proceed with dataset D2 and try to find out which node we will be selecting for splitting the node. We proceed with D2 and calculate the entropy and information gain corresponding to attribute A2 and A3 respectively. We get the information gain corresponding to A2 as 0.36. Just remember that whenever we are going to calculate the information gain corresponding to A2 at this stage, we need to consider the entropy of parent node as 0.7616, which was the entropy of A1 we calculated in the first iteration, and I think it's pretty much clear by now after like 2-3 video lectures which entropy to pick. Similarly, if we try to calculate the information gain corresponding to A3, we proceed in the same way, that we first arrange the distinct values in an ascending order, and we find out the split points and discard the extreme split points in this case because the root node has already been created, and calculate the information gain. Over here the maximum information gain is 0.3616, which is obtained when the split point is 4.5. We see that we get the same information gain corresponding to A2 and A3, but for a change we will select A3 and use 4.5 as a splitting criteria. This results in two subsets of D2 again. One will be a pure node and other will be D4. Let's see what happens when we split on A3. So over here we can clearly see that we get a pure node over here, and we clearly get a pure node over here because all the values corresponding to target are 0, and over here all the values corresponding to target were 1. We were left with two data sets, D4 and D3. We can calculate the information gain in the usual way, but since the number of data points in D3 and D4 is pretty less, we can skip the step and get the final decision tree, which will look somewhat like this. So corresponding to the given data, we get the final decision tree over here. We can check a few examples to see what we get. Now, if let's say we consider A1 to be false, and we consider A2 to be equivalent to true, and A3 to be equivalent to, let's say, 9, and we need to check what class we are actually getting. Now if A1 is false, then if we go to the decision tree, we will probably be here because A1 is false, and since over here we need to check the value of A3, the value of A3 is 9, and this is actually above 4.5. We will follow this path, this condition gets satisfied, and this gives me a root node, or sorry, a leaf node whose outcome is 0. So the outcome of this data point will be 0, or it will be a negative class. Similarly, if we consider A1 to be equivalent to true and A2 to be equivalent to false and A3 equivalent to 8, this is how we will proceed. We know that A1 is true, then we have to take this route, and over here we need to check what value of A2 we are supposed to have. A2 is actually false. We are going to take this route and select false over here, and now it needs to check for A3. The value of A3 is above 6, which is 8. And since this condition is satisfied, we get the outcome as 1. So based on this, we get a positive outcome. So we make an important observation here from the final decision tree obtained. The entropy of each parent node at each successive step keeps on decreasing. For instance, if A1 is a parent node and A1 is a parent node to A2 and A3, the entropy was 0.76. A2 was a parent node to A3 and this was a leaf node. It is having an entropy of 0.5, and the leaf node obviously will have an entropy of 0, and A3 will again have an entropy of 0. Similarly, A3 over here is having an entropy of 0.4. So what we can see is as we grow more and more leaves, the entropy keeps on decreasing. So in the next video, we will prove mathematically why the entropy keeps decreasing after splits are performed in a decision tree, proving that information gain is always positive. Thanks for your time.